if you're doing functional Scala, surely you have come across monads, and it's likely that you have come across this claim as well, that monads are about sequencing. But what does it even mean? It could mean just that we get a syntax that when we write monadic programs, it looks like writing a sequence of steps. But certainly there's more to that, because monads are not unique in having a sequential pattern of composition. Functions already can be composed sequentially, or monoids, it's a sequence of elements that can be combined. So surely there's more to that claim. Could it mean that when I write monadic programs that it enforces sequential execution? Or sometimes people say it guarantees the order of effects as we see them in the code. They will be in that order on the output or execute in that order. And here's the spoiler. I'm claiming that the only defensible claim of these is the first one. The other properties could be properties of some specific monads of a specific language, but those do not hold generally about monads. Anyways, let's do a quick refresher. For type M to be a monad, we require that it supports mapping over the monadic structure. It supports lifting a pure value into the structure, and that it supports flattening multiple layers of a structure into a single layer. And we can derive flat map from these, or just take flat map and pure as primitives and derive map and flatten from those, whichever you prefer. And there are some monad laws, but let's not worry about them for now. And then in Scala, we would also like the dot notation to get the map and flat map directly on the structure MA. We can do that via extension methods that then works nicely in for comprehensions. Or another extension method to compose functions that return a monadic value sequentially, or apparently sequentially. So if I have two of those, we can compose them in a point-free way. Okay, let's see it in practice. This is what our monadic code could look like, using a for comprehension or the so-called Kleisli composition in a point-free way. Here we see a sequence of steps, and for G to be able to apply G to B, first F would have to finish and produce B. So, of course, this is sequence, right? This is a sequence. And even at the type level, we see a sequence. So monads are all about sequencing, right? Well, no, not really. But in order to see that clearly, let's first expand our concept of a monad. It turns out that this definition that we saw before is too specialized to Scala functions. So let me do some adjustments. First, let's just flip the arguments. That's not of map and flat map. That's not changing anything. And now let's change the method so that all of them return a function. Just some syntactic manipulations so far. And now let's abstract over the Scala functions. So everywhere where we now see the Scala arrow, we replace it with an abstract type parameter, some abstract arrow. And we're going to require a little bit from that arrow, but really not much. Just that it is a category. But what's a category? It just means that we get sequential composition of arrows, and that we have identity arrows. Okay, so what else could be a category, could have these operations other than Scala functions? Yeah, and before that, maybe an arrow is too suggestive that there's an input and output. You could, for all that matters, use a different symbol that's not suggestive of any direction of flow. A subtype relation, this comes from Scala standard library, forms a category. Can we compose them? Yes, and there's already a method in the standard library for that. And every type is a subtype of itself. So we have a category. What would monads look like in this category? So for a type M to be a monad, we would have to implement the methods. Let's look at them. Mapping means that if A is a subtype of B, then M of A is a subtype of M of B. That means it preserves this relationship. In other words, it is monotone. What does pure mean? It means that M sends any type to its supertype. This is called extensive. What does flatten mean? It means that if we apply M twice, we don't get any further than if we apply it just once. This is idempotence. And these are exactly the defining properties of a closure operator on a partially ordered set. Let's visualize that. So this is the lattice of Scala types. There's nothing at the bottom, any up at the top, and then there are some types A, B, M of A, M of A, M of B. Now, if we have evidence that A is a subtype of B, let's visualize it in the lattice. The arrow here does not have any computational content. It's just a statement that A is, in fact, a subtype of B. Now, mapping, or monotonicity, means that this relationship transfers to M's. M of A is a subtype of M of B. Then we have pure. That is, A is a subtype of M of A, but also applies to B and applies to M of A. These are, again, just statements that one type is a subtype of another. And what does flatten look like? Gives us arrow in the other direction, and meaning that M of A and M of A are the same type. Okay, let's bring some concrete M. So this was some abstract M. Can I give an example? Let's define a result, something like a result type, which could be A or an error. This would not be a monad in the category of Scala functions, but here it is monad. Can we implement map? Yes, this subtype relation has a method to lift it to any covariant type constructor. What's pure? Just expand the definition, and then it becomes an immediate fact of the Scala type system. What about flatten? Yes, same thing. Immediate fact of the Scala type system. Did anyone spot any sequencing here? Not myself, but if anywhere, it would be in flatten, right? Because that's the special thing about monads. But remember, flatten is just the statement that one type is a subtype of another type. There's no execution. There's no effects. It's just a statement. Right, so lesson so far, monads can be defined in any category, not just the category of Scala functions. And that's all that you need to know. There's no sequencing, right? I can end right here, but since this is fun, let's play again. This time I'm going to give you something with execution. Consider this wrapper of a function, but with the reverse order of type arguments. You can give it a convenient type alias, the opposite arrow, and now the question is, can we compose these arrows? Is this a category? And yes, this is the category that's opposite to category of Scala functions. Can we implement composition? Sure. Can we implement identities? Sure. What do monads look like in this category? I could try to sound smart and say that monads in this category are exactly the comonads in the category of Scala functions, but I'll keep things simple. Don't worry about comonads. I'll use the identity functor, which is both a monad and a comonad, both in the category of Scala functions and the opposite category, which is just the wrapper for a value. Also, our monad implementation for it is straightforward. Don't worry about the details, but just very straightforward. So let's run something with it. This is now runnable code. There will be execution. Let's define some initial functions. The important thing is this can be chained. If the first one ends in Boolean, the second one starts with the Boolean, and so on. And I've just added some debug prints here to see the order of execution. And then we can use the syntax that we defined previously, the Kleisli composition, and compose the arrows and then run it. What's the output going to be? See, we're printing something here. The output is exactly in reverse order. So like where's the sequencing? I would expect first F, then G, then H, but this is exactly reverse order. We could do for comprehension, run it, but the output is again the same. So this is counterintuitive, yet it's a lawful monad that does not execute in the order that we see it in code. Right, so the lesson is that although we have syntax that gives us a sequence of steps that may have no bearing on the execution. So, game over again, right? But yeah, there will be, maybe I'm just misunderstanding it. It's not about execution order or sequential execution. It's about the effects that are sequenced. And those print lines that I had there, those are not proper effects because they are too unhinged, they are unmanaged. It's the monadic effects that are sequenced, right? Okay. So and the flatten, because that's the special thing about monads, is what sequences these mysterious effects. Notice how sneaky this statement is. So it's assuming that somehow there's an effect associated with each monad, okay? And that then it is somewhat well-defined and precisely defined what sequencing means, which it is not. So it's a very vague statement, and as any vague statement, it's open for reinterpretation, and it will be reinterpreted against you. So the right thing to do is just reject this game and demand clarity. But since I'm too gullible, I'm going to play this game some more. Let's look at the writer monad, which is a common monad. Writer monad is, in addition to producing a value A, it outputs some log messages. And then flattening needs to combine those logs into a single log. So the effect of this monad would be writing items to a log, and the sequencing here means that the messages will arrive to the log in the order that we see in the code. Here's an example. If we output first fun, then Scala, then 2023, the flattening does the obvious thing, and we get them in the same order. Here's the twist. The writer monad is a valid monad for any lawful monoid, such as this list and concatenation. So what about this monoid? The important thing here is that the input lists are concatenated in reverse order. Is this a valid monoid? Yes, you can work out that it's associative and that empty list is still the unit element. So yes, it is a lawful monoid. So when we use it in flatten, what does it look like? Oh no, we got the reverse order. We said that the innermost is now the first one, but we have claimed that the outer effects will be first. Well, what to do with that? But as I said, it will be reinterpreted against you, so a staunch defender does not just give up and come up with an explanation. The effect of that monad with that flatten is prepending to the log. Told ya, effects are all about sequencing. So let me get that straight. So effect is the monad itself, and sequencing is whatever flatten does. Well, congratulations, you have a bulletproof definition. Cannot argue against that. But it's also tautological and completely useless. Okay, so we get that sequencing of effects is not precisely defined and can only be defined tautologically. But people will be insisting that it is sequencing. What we saw is sequencing, doesn't matter, it's in reverse order. I think the right thing to do is just to say no and don't feed the trolls. But yeah, I'm too gullible. I'm going to accept the game and continue. So up next will be a concurrent and non-deterministic version of the writer monad. But first, let me give you a quick intro to Libretto, which is a DSL for concurrency embedded in Scala. Where in Scala we have pairs. In Libretto we have concurrent pairs. We'll see in a minute what that means. It has an analog of either, this plus symbol, but meaning is closer. Think of it more as if it was wrapped in a future, like resolved later. It's going to be resolved later whether it's left or right. And there's a unit type. Functions in Libretto are linear. There's a principled way to do promises. Here's how you could define list in Scala. It is either empty or has an element and the rest of the list, and it translates directly to Libretto. Either empty or an element and the rest of the list. But let me give you some intuition for the list. Anytime in Libretto is an interface of interaction, and I will show below the horizontal line what has already been observed by the consumer of the list, and above it is still unknown to the consumer. Let's expand the definition of the list. And now, as we don't know whether it's left or right, but as time passes, it will get resolved. Let's say it's right. So there's an element, and we have concurrently the element and the rest of the list. Let's call the element A1 and continue with the tail. It gets eventually resolved. Let's say there's another element. Let's call it A2 and continue until eventually we hit the end of the list. All right, let's visualize concatenation. Nothing tricky here. If we have two lists and want to concatenate, then we first only observe the first one until we hit the end of the list. Discard the unit there. Unit is one of the few things that can be freely discarded in Libretto, and just connect the second list to the end. Okay, and this forms the usual monoid on lists, but what I want to get to is a concurrent merge of two lists. So now we will concurrently be observing both lists, and so there's some racing, and whoever gets resolved first wins the race. So in this case, it's the second list. So we have uncovered an element there, move it to the output, and continue racing the two lists. Then the first list wins, there's an element, we move it to the output and continue and race again. Now the first list wins again, we output its element, race again, and so on. We uncover another element, output it, and we continue. Now we have reached the end of one of the lists. We discard it and connect whatever is left as the tail of the list that we are building. Okay, so let's merge. So this is what we had, merge the two lists with this result. And it appears, so we could say loosely that this merge preserves the temporal order of how the elements are appearing. So could this be a monoid? In particular, could this be associative? That means doesn't matter if the order of merging, if we are merging three lists. It certainly does appear so because this preservation of the temporal order seems to be invariant of the order of how we merge the lists. But how do we even define that equality there? Especially because it's non-deterministic and it could have many different outcomes. Remember, there was this racing, and it's concurrent, and it's not deterministic who wins the race. So these are all possible outcomes that could have come out, and the only guarantee is that within the input lists, the order of elements is preserved. Okay, so let's. So what does it even mean then to for two non-deterministic functions to be equal? For deterministic functions, we usually say they agree on the same input. For the same input, they produce the same output. We could say it slightly more generally that they have the same observable behavior, but the only observable is the output. What about non-deterministic functions when there are many different possible outcomes? Let's say, and relying now on the intuition of what's an observable behavior, that they have the same set of observable behaviors. So let me give you how we could reason that it's associative. Consider any possible outcome of the left side and reason that it's possible to get it on the other side. So let's say merging A's and B's produced this sequence, and then we merge it with C's and obtain this sequence. And the question is now, could we have obtained the same result on the right side? On the right side, we first merge B's with C's. Those are these elements. Let's pull them out, and the question is, could we get this sequence? Well, sure. We have just seen we can get any sequence that preserves the order of relative order of the input elements of the input lists. And then if we merge it with the other list, could we get this same sequence? Well, by the same argument again, it's possible to get the same outcome. So we have reasoned that merge is associative by this intuition. Empty list also works as a unit for left and right unit, so we have a lawful monoid. All right, now back to our writer monad. What does it mean for the writer monad? It means that now we are using the libretto types, otherwise it's the same, and we'll use merging to combine lists, and since it was a lawful monoid, it is now a lawful monad. Flattening now does the non-deterministic merge of these individual logs. Think of it like you send a message to log, send another message to log, you send another message to log, and on their way to log, they are racing, so they could arrive in different orders, yet it is still a lawful monad. So yes, please, where's the sequencing here? I'm sorry, but there's really just no sequencing. Yeah, so lawful monads do exist even in non-deterministic settings. Summing up the lessons in other words, monads do not require sequential execution or any execution at all, as we saw with the subtype relationship. They do not require ordering of effects and don't even require determinism. Monads are not about sequencing. A few final remarks. When we see that monads do coincide with some sequential execution, question for you, where does it come from? It's not a general property of monads. We'll leave that for you. If monads are not about sequencing, what are they about? We don't need to be mystical about it. Flattening is the special thing of monads, and it lets us simplify an arbitrarily nested structure into a single level, and that, to me, is already powerful and beautiful enough without other false intuitions. I get that it might have served us as a useful crutch to understanding monads, that monads are about sequencing, but eventually we are better off without crutches. And finally, there raises a question, what else are we wrong about? And with that, thank you very much.